So let's take a look at something called Jordan Decomposition, which is an extremely powerful tool to decompose an endomorphism of a vector space over an algebraically closed field into two really nice pieces that have a lot of nice properties. And we're actually going to generalize this notion to something called abstract Jordan decomposition, which is even more useful. So, well, that will be for later, but with that in mind, let's recall from linear algebra what a Jordan canonical form is. So if V is a finite dimensional vector space over an algebraically closed field of arbitrary characteristic, then for all x in end V, there exists a basis in which x is block diagonal. And in particular, the blocks are called Jordan blocks, and they're very nice behaved, which is the block themselves just consist of eigenvalues, the same eigenvalue repeated along the diagonal and then ones above it. And of course, if the Jordan block is 1 by 1, then there's no space for the ones. But other than that, what this is basically saying is that x, you can if you're forced to determine a basis for V in which you have to work with x, you might as well pick this basis in which it's basically almost diagonal. And in many cases it is diagonal, right? If the eigenvalues, if you have eigenvectors that span, I guess, the entire space. And so what's really nice is that, at least the key idea we'll be focusing on here is that if you look closely, this Jordan block is really some constant, the eigenvalue times identity matrix plus a strictly upper triangular matrix, which is nilpotent. And because each block is like that, that means x is the sum of a diagonal piece plus a nilpotent piece. And that's the idea we're going to seek to mimic and actually formalize that notion. And so as a quick review, what is the characteristic polynomial of x if I'm telling you that each block, Jordan block here, has dimension Ri by Ri? Well, that would just be the product of the determinants of each block once you subtract off some indeterminate times the identity. And so it's an easy check. You should know this already, which is it's just simply t minus lambda I to the Ri all multiplied together, ranging over the i's. So keep this in mind. Keep this picture of the Jordan blocks and x represented in this form. Keep that in mind. And so with that being said, let's take a look at some definition of facts. So we say an endomorphism of V is semi-simple if its minimal polynomial has distinct roots over f. So we can't repeat roots. However, because we're algebraically closed, we can just say this is equivalent to diagonalizability. You are diagonal if and only if, or you can be made diagonal if and only if you are semi-simple. So just think of semi-simple as diagonalizability. So with that definition in mind, we have three facts. The first one should be familiar, which is if x and y are simultaneously diagonalizable, then they commute. And the converse is true if both are diagonalizable. It's entirely possible that two matrices commute and then one matrix just gives up and it's not actually diagonalizable. So you require both matrices to be diagonalizable. So with this in mind, it follows that if x and y are both diagonal and commute, then their sum is semi-simple, simply because there's a basis in which they're both diagonal. And so you just add them together, and then it turns out x plus y is diagonal, right? And then lastly, which is really easy to see, is if x is semi-simple, and then it stabilizes a subspace of V, then x's restriction to that subspace is also semi-simple, right? So these are three easy facts, and I think two of them should be obvious, and one of them should be evident from what we learned in linear algebra. So with that being said, we have our Jordan-Chevalley decomposition. So let V be a finite dimensional vector space over an algebraically closed field, and let X be an endomorphism of V. Then there exists unique XS and XN in NV such that XS is semi-simple, XN is nilpotent, and X is the sum of the semi-simple part and the nilpotent part, and XS and XN commute. By the way, this exclamation point here denotes uniqueness. And this is an extremely strong statement. These pieces are so nice. XS is basically diagonal and XN is nilpotent. So it'll pretty much, if you raise it to some power, right, X, you got both of these pieces are really easy to exponentiate and study. And so this decomposition here is called the Jordan decomposition. And part A is really what's critical and what we're going to prove. Part B and C kind of follow naturally, actually from the proof. So part B simply states that there exist polynomials P of t and Q of t in some indeterminate t, such that if you stuff in x into P and then stuff in x into Q, xs is P of x and xn is Q of x. And P and Q have no, the additional caveat is that they have no constant term. And so what this implies, right, is that if you have two polynomials in X, the two polynomials are going to commute, and then that also means that they're going to commute with everything that commutes with X. So that's nice. And then the last thing here is that if A is a subspace of B is a subspace of V, and X sends B into A, then XS also sends B into A, and so does XN. And that's really nice is because if you have X acting on some vector, and then you study XS acting on that vector, and also XN acting on that vector, they're both going to live in the same space that X is sending things into. So that's nice. And so the way we're going to prove this is to use, actually, rather than I'd say like induction or more linear algebra techniques, perhaps, we're going to use abstract algebra here. And so the idea is something called the Chinese remainder theorem, and we're going to solve an equivalence, congruence relation, and find a solution for that. And so you might remember, right, if you ever did like math counts or some math contest, right, you might be asked to solve the congruence. X congruent to 1 mod 3, X congruent to 7 mod 11, and then X congruent to, I don't know, 9 mod 16. Right? And what the Chinese remainder theorem says is that if each of these guys are pairwise relatively prime, there exists a solution to this system, these congruence relations. And furthermore, there exists one unique solution up to scalar multiples of the product of these guys. So it's X exists, and then of course X plus 3 times 11 times 16 is a solution, and so on. And so if I change the 16 to say the 22, then you're not guaranteed a solution anymore because they're not coprime. And so that's just the Chinese remainder theorem, and on integers, on the ring of integers, and so we're going to extend that to the ring of polynomials. And so that's just some background. Let's actually get into the proof. So let lambda 1, lambda 2, dot, 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 lambda k, so let's draw a line here, lambda k be our eigenvalues of X, and so X is the endomorphism of V that we're studying. And then let it have multiplicities, M1, M2, M3, and so on. So M1, M2, dot, 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 Mk. Okay? So the characteristic polynomial is clearly given by C of t is equal to the product of t minus, or let's use capital T, t minus lambda I to the mi, where I equals 1 to k, right? And you can just think of the Jordan blocks. That's probably the most intuitive way to think of this thing. And so this is our characteristic polynomial. And so now we're going to look at our generalized eigenspaces corresponding to each eigenvalue. So we have define Vi is equal to the kernel of X, our endomorphism, minus lambda I times I to the mi. So this is another endomorphism, and this is actually our generalized eigenspace. And so this should also be familiar from linear algebra. I've attached some reference notes if it's not. And I've also, I think, there's going to be something about Chinese remainder theorem in there as well. And so this is going to be our generalized eigenspace. And what it's saying is that this is all vectors that get sent to 0 under this thing, right? So remember that. This thing sends things to 0. Whatever is in here gets sent to 0 by this thing to the mi. Okay, and so the restriction of x, to v sub I has characteristic polynomial let's see, it has characteristic polynomial c sub I of t is equal to the product of, well, no product here, it's simply t minus lambda I to the mi, right? And that should be easy if you just study, if you just look at all the Jordan blocks that have that represent a common eigenvalue. And so this is the restriction of x to vi's characteristic polynomial. And so now is where we're going to define our congruence problem, similar to what we saw earlier, right? And so define the following congruence relations. Following congruence relations. So the thing that we're hoping has a solution, we're going to call it the polynomial p of t. So this is, rather than being a congruence relations over the ring of integers, we're doing it over the ring of polynomials over our field. So so we're going to define this as p of t is congruent to lambda 1, our first eigenvalue, mod the polynomial t minus lambda I, m sub I. So this is our characteristic polynomial over vi. And then we're going to just do it over and over again. So this thing that we're looking for satisfies all of these congruence relations. Or so this should be a 1 here, right? This should be a 2, and so on. And then this becomes p of t. This is congruent to lambda k mod t minus lambda k to the m sub k. Okay? And furthermore, if 0 is not an eigenvalue, we're going to add the last relation, p of t is congruent to 0 mod t. Okay, and this is just to stipulate that p of t has no constant term at the end. And I hope that gives you a hint as to why x sub s will not have a constant term and why q of s won't have a constant term. So anyways, where are we now? So what we're going to do is we're going to apply the Chinese remainder theorem. Apply the Chinese remainder theorem. And why can we? Because in the same way that those integers in our integer case of the congruence relations were all co-prime, these guys here, these polynomials here, are all co-prime. And so this notion of co-prime really is that if you think of it as over the complex numbers, is that they don't share any common linear factors. And so in general, really what it means is that they share no irreducible factors. Over the complex number, the irreducible polynomial is the linear polynomial. So regardless, is that they're all co-prime per se, and so that means there's a solution to these congruence relations up to some multiple of all of these guys. So apply CRT to get P of t existing. Okay, so now we have P of t and it satisfies all of these things. And once again, I have a link. I'll have a link to the Chinese remainder theorem in the description. So now define x sub s is equal to p of x, and then x sub n is equal to x minus x sub s. Okay? So I hope you see right away, right, that x of s, or actually let's just say it the way they do in the book. So I'm consistent with what I said. So define the polynomial q of x is equal to x minus p of x, and then let xn be defined as q of x. Okay? And so what we've done here is that we've shown, let's go back up to the top here, all the way here, that there exist polynomials q of t and p of t such that xs is p of x and xn equals q of x. So this is kind of cheap in the sense that we're doing this by definition, right? Oh, there exist polynomials. Well, of course, because that's how we're defining them. And p and q have no constant term. Well, that's because of that last relation we stipulated, which was that this polynomial is congruent to 0 mod t, so it can't have a constant term. And so because xs and xn are polynomials in x, they commute with each other. And so it also follows that they commute with everything that x commutes with, right? Because these things are just powers of x times some constant added together. Okay? So we kind of got b here, right? Now, so because we have b, right, then we get c as well, right? Because xs and xn are really just, once again, they're just polynomials in x. So we have b and c, but what we don't have yet is the real meat of the theorem, which is that that xs is semi-simple, xn is nilpotent, it's unique, and well, of course, x equals xs plus xn. We have that, right? So going back down here, just by the way we defined xn, we have xs equals p of x, and xn equals x minus p of x. So if you add the two, of course you're going to get x. So the two things we have to show now are semi-simplicity of xs and nilpotency of xn, and then of course we also have to show that uniqueness. Okay, and so semi-simplicity of xs follows very naturally, right? So xs is equal to p of x, right? And we said p of x, so what this means is that xs minus lambda I times I for any I is equal to p of x minus lambda of I times I, right? But we said that p of x up here, right, looking at some arbitrary I, so let's say I equals 2, is congruent to lambda 2 up to some multiple of t minus lambda 2 to the m2. So their difference is going to be a multiple of this polynomial. Oops. So coming back down here, this implies that xs minus lambda I times I is equal to some polynomial in x times x minus lambda I to the mi. Now, of course, what that means is that, recall that if this endomorphism here acts on v sub I, right, by the definition of v sub I, these are all the things that are in this guy's kernel, so you're going to get 0. So it follows immediately that this thing acting on v sub I is also 0. So xs acting on each of our generalized eigenspaces is diagonal, and so what that means is xs overall is diagonal, and so that means xs is semi-simple. So xs is semi-simple, and so now by our Jordan decomposition, right, xs is that semi-simple part, we're just subtracting it out, so xn is going to be our nilpotent part. And so that shows the semi-simplicity of XS and the no-potency of XN. So the last thing to show is that these pieces are indeed are unique. So actually, I want to be a bit more explicit about this piece. So this is XS minus lambda I, I guess restricted to VI is equal to 0. So XS restricted to VI is equal to lambda I restricted to VI. And so it's block diagonal, but the blocks themselves are diagonal, and so XS is diagonal. So now let's look at uniqueness. So suppose XS plus XN is one Jordan decomposition for X, and then the other one, X twiddle, X of N twiddle, is equal to another Jordan decomposition. Well, if you subtract the two and rearrange just a little bit, what we're going to have is that, so let's do XS minus X of S twiddle is equal to XN twiddle minus XN, right? And so now we're going to apply those facts we talked about before our theorem, which is that this guy here, so each thing here is a polynomial in X, so they all commute with each other. And so this guy's diagonal, so and they commute with each other. That means that this thing here is also semi-simple. So the difference is semi-simple. So this entire piece here is semi-simple. Okay? And similarly, this thing is nilpotent, this thing is nilpotent, and since they commute, their difference is going to be nilpotent. I think we looked at that in an earlier video. And so this entire thing is nilpotent. But the only matrix, or the only endomorphism that is both semi-simple and nilpotent is 0. So that immediately proves uniqueness. That says the XS equals X twiddle S and XN equals X twiddle N. So there we have it. We have the Jordan decomposition of our X. And so this is actually, I really like this theorem because the Chinese remainder theorem is really shines here, and it just gives us so much strength. And we'll see later on that it's very useful. The abstract Jordan decomposition will be useful when we talk about like the universal enveloping algebra. It's a very powerful notion. And so with that in mind, there are a few lemmas that that are introduced in the book. I won't spend too much time here because I think the second lemma, for example, is used like in one proof somewhere. So I guess I just outline the proofs. So lemma A is pretty nice, and actually I take that back. Lemma A is pretty important, but maybe not so much in lemma B. But anyways, so if X is an endomorphism of V and has a Jordan decomposition given by X equals X sub S plus X sub N, then the adjoint of X has the Jordan decomposition in end V of where you simply take the adjoint of XS plus the adjoint of XN. And that doesn't seem entirely, like it's not entirely trivial, really, that it works out this way, but it's pretty nice. And so cross this out. I was going to prove this, but I didn't feel like proving it. So add X is semi-simple. And so the way you can show that add X is semi-simple, and so of course this will be our semi-simple piece and this will be our nilpotent piece. And so the way we can show add X is semi-simple is fix a basis for V in which X is diagonal, XS is diagonal. And then just in the standard basis for GL of V using the basis vectors E sub ij. So remember these guys, E sub ij. The basis for GL of, I guess in this case, end V, right? Once you fix a basis for V, or rather for end V, you can compute that, you can just do the computation, compute the matrix of add XS, and you'll see it's diagonal. So this is check. Add XN is nilpotent. We saw this in an earlier video, I think on the one on Engel's theorem. And then because X is equal to XS plus XN, add x is equal to add x plus add xn by the linearity of add x, right? So this is nice. And so lastly, because adjoint is a homomorphism, and because x sub Sn and x sub n commute because they're the Jordan decomposition for x, the adjoint of 0 is going to be 0. So the adjoint of xs bracket with the adjoint of xn has to equal 0. And so we have these things here. And so we conclude that by uniqueness, right, this is the Jordan decomposition. We found two things that happen to satisfy everything in our theorem. So because we showed uniqueness just now, then they have to be our Jordan decomposition. And so the last statement is also will be used like in a proof, I think in section 5. And so this lemma states that let U be an algebra, so it's just going to be some vector space endowed with, I think it's an associative algebra, so it's going to be endowed with an associative operation. Or maybe it's not, but regardless, it's going to be some operations. For example, the matrix algebra is an algebra. And so let delta be an element of the derivations on U. This lemma states that, well, if delta equals sigma plus, I think this is nu, sigma plus nu, then both sigma and nu, if they're the Jordan decomposition, they also live in dir U. So this is actually something in NU, right? Like dir U is contained in NU. And what's nice is we're saying is that the derivations semi-simple part, which it's going to be sigma, and its nilpotent part also are derivations. And so the way we're going to do this, I've written it here, but we're just going to outline it. It's pretty straightforward. We're going to basically introduce our eigenspaces again for U, and which is basically going to be everything in U such that when delta acts on x with some sufficient power, or delta minus f sub I acts on x with some sufficient power, it's going to be in the kernel, basically, of that map. And so in particular, like we saw earlier, right, if the f sub I are the eigenvalues of delta, then U is going to decompose into the direct sum of the kernels that range over the eigenvalues, where f ranges over the eigenvalues. And so because sigma plus nu is our Jordan decomposition, we have that if the f sub I are eigenvalues for sigma, they're for eigenvalues for delta, they're eigenvalues for sigma. So sigma is going to stabilize U sub fi, and it's going to do so in a constant fashion. Well, yeah, that's obvious because it stabilizes it. Anyways, so yeah, that's that. And so furthermore, I guess a small fact we'll need is that U sub f times U sub g, so these are two of these kernels slash eigenspaces we defined above, are, when you multiply them together, they're contained in U sub f plus g. And so the way we can see this is to use the fact that delta is a derivation. So if we have something that's an element of f plus g, so if it's an element of this thing, or I guess our goal is to show that if x is in here and y is in here, and then we take, we're trying to show that x times y, where x times y is the operation endowed upon our algebra, is going to live in this thing here. And so we're going to effect an identity that I don't feel like proving, which it's really easy to prove. It's just use induction and then use the fact that delta is a derivation. And so we call it the derivation property here. And so what we have is that delta minus f plus g times I, right? So this thing, this thing, right, is how we define that thing. Acting on xy is going to be is given by this almost like a binomial theorem here, and what we realize though is that delta minus f sub I, well, since x is an element of u sub f, and y is an element of u sub g, if I choose n large enough, then x is going to get sent to 0 by this matrix, or y is going to get sent to 0 by this matrix. But regardless, if I choose n large enough, each term in the, at least one of these terms will be 0, so their product will be 0, so everything in the sum is going to be 0. And so it follows that this thing on the product xy is 0, so that means xy is an element of u sub f plus g. Okay? So now let x be in, let fi and fj, as we noted, were eigenvalues, so let x be in fi, u sub fi, and let y be in u sub fj. So sigma, which is our semi-simple part of xy, right, is going to be an element of f sub I plus f sub j times xy, because we said that sigma acts on these spaces in a scalar multiplicative fashion, right? And because xy is an element of u sub fi plus fj, as we just saw up here. And so note that by the derivation property, right, this thing here is also equal to this, just applying the derivation property. And so what we have is that so yeah, so we show this, that this piece is equal to sigma sub xy. And so since u is a direct sum of the eigenspaces, it shows that sigma is a derivation. So this step right here is just verification that sigma is a derivation. So my bad, I kind of forgot what I was doing here. That's so yeah. So here, this step we show is derivation. So anyways, that's kind of like a convoluted way of showing that sigma is a derivation. And so going all the way back to the top, we show that, where are we? That sigma is a derivation, right? And we know that delta is a derivation, so it follows that the difference of two derivations is going to be a derivation, that nu is a derivation. And so that proves lemma B. So just to recap, the most important parts, or here we are, the most important part is this. There exists this Jordan decomposition, and they commute, and one piece is semi-simple and one piece is nilpotent. That's what you need to really take away from this, and we'll be using that a lot. So I think that's going to conclude this video on Jordan decomposition. I think we can move on to, I think the next one will be Cartan's criterion. So thank you for watching this video.